good evening, everyone. My name is Chișcariu Radu-Emanuel, and I'm a security researcher at Keysight. And tonight I'm going to talk about one of my fuzzing projects, and more exactly about how I have found my first vulnerabilities this year. So first I want to ask everyone in the room if you ever heard about fuzzing. Please raise your hand. Please don't be shy. Okay. Okay. So a lot of you guys heard about fuzzing, but who of you ever actually tried to fuzz something? For example, an application or? Okay, cool. So this is the place to be. So fuzzing it's about throwing, let's call it pseudo-random, if there are cryptographers around here, input at applications and see how the application behaves. It is a very useful tool, both for the developer and for the security researcher and for the black hat, for the hacker, because if the first one prays not to obtain anything with the fuzzing, not a corner case or a bug or actual vulnerability, then the attacker preys on that. He wants as many bugs and vulnerabilities and crashes as possible from fuzzing. What is cool, another thing that is cool about fuzzing is that the current state-of-the-art software that do fuzzing are very complex, and they do a lot of cool stuff, which we are going to talk about. Also, the interesting thing about fuzzing is that its results are, let's say, neglected by management, and by that I mean if you find something in a library that your project employs, then it won't be a very interesting thing. You would be asked to continue something else with a lot of importance, and that's how events like Equifax breaches happen. Before going into the actual fuzzing, it's important to make some distinctions. There are different strategies, way to conduct fuzzing, but I've separated the, let's say I have this classification for you, which is we have on one side we have evolutionary based fuzzing, in which we employ genetic algorithms in order to come up with a certain input that will try to go as far into the code. So how fuzzing actually works: if we have an application that accepts an input and do some kind of conversion and parsing of that input, then with evolutionary based fuzzing, we will be pretty much oblivious of the file format, and we will just try to come up with it along the way, so to speak. So we will use different mutation strategies in order to do that, to reach as far into the code as possible. Current state of the art is held by tools as American Fuzzy Lab, libfuzzer, and HongFuzz, something developed by Google. This is approach that is, let's say, opposed to the generational based fuzzing, in which we come up with an input for the fuzzer by respecting a certain set of rules. So we say, please don't fuzz that because this is important. For example, it's a set of magic bytes for the file format, but fuzz this and come up with an input. And the idea here is to reach further into the code because we respect those set of specification about the file format, and I don't know, reach maybe interesting further into the code in more interesting corner cases. So as the fuzzing workflow, first we will feed the test case into the application. Then you will observe the trigger path, and this is done with instrumentation. Who heard of instrumentation from here? Please raise your hand. So what instrumentation essentially does to a piece of code that is compiled with that is it will insert certain pieces of code during our project, and when that application is run, it will inform, let's say, the fuzzer application that you use of the state that you've reached, how further you've reached into the code. And this is useful because the idea here is to use different mutation strategies in order to reach further into the code. Okay, so we observe the trigger path, then you modify the test case accordingly and check if that modification allowed us to reach further into the code. If that is not the case, then we modify the mutation strategy and try something else and see what happens. So as you can see, this is a cyclic process, and the current fuzzers allow us to completely automate this. And this is also one of the reasons that I like about fuzzing, because if something if the TL looks and asks me what I'm done, I can say I'm not slacking off. My application is fuzzing. So as we saw earlier, there are a lot of fuzzers, and I've chosen to conduct my investigation using American Fuzzy Lab, which, except of being a rabbit breed, is a fuzzer developed by Michael Zalewski, which is a Google security researcher. He came up with this amazing tool that employs genetic algorithms in order to do fuzzing, so it's genetic based pretty much. What I like about AFL is that it's very easy to set up. It has a very good handling of crashes and hangs of the application, and of course, last but not the least, it has a huge trophy case of found vulnerabilities. I mean, in OpenSSL, ImageMagick, you name it, if you go to the page, you can find a lot of vulnerabilities, and those are just the only that were reported back to Michael Zalewski, and he updated the page, but there are a whole lot more. I mean, I look a lot at different projects and their bug pages, and a lot of them are found using AFL, so it's a very much employed tool. Now we have the fuzzer. The next thing is to choose an application that we want to fuzz, and I've stumbled upon during my searches on SDL. Another thing that is very hard for fuzzing is to find something that wasn't fuzzed before. So if you start, so those from this room that did fuzzing, you feel my pain. So this is a very interesting library, because as you can see, it was employed to create games and engines and different kind of application. It was actually used for the Cry engine, which, as you might know, it was used to create the game Far Cry for those gamers that are in the room. Also, it has a lot of functionality. You can even handle sockets with this library, so a lot of functionality equals for security researchers, a lot of things that could go wrong. Let's do that. Okay, now we have the fuzzer, we have the application. Let's go and start to do the preps for the actual fuzzing campaign. The first thing that you do, you download the sources of the application that you want to fuzz, and you compile them with the AFL wrappers for GCC. So what this actually does, except for the compiling part, it adds that layer of instrumentation that we talked about earlier, which will inform the AFL process where exactly you go with that input that you serve. Another thing that we do is we compile the sources using this flag, fsanitize equal address. What this does is effectively allows you to compile the sources using address sanitizer, which is a memory, which is a tool for C projects that allows you to find memory-related issues, which those juicy ones that the security researchers love, as for example, use after fee heap, based buffer overflows, and so on. So why the white paper of the address sanitizer states that during their tests, they saw that adding this layer, the supplementary layer of instrumentation, makes the application runs 2 times slower. But we want to do that because we want to find also this kind of corner cases. Now, after we successfully compile, actually that's another pain that those who want to do fuzzing experience. It's pretty much, it's sometimes very hard to not create a conflict when you're using the AFL wrappers and also the other sanitizer. But we successfully did that. Now we're trying to make a test harness. So what is a test harness? Is essentially a piece of code that we write in order to fuzz the library indirectly. So what we're doing here, what we're trying to do here is we're trying to fuzz a call to that library. And the test harness is pretty straightforward. We initialize the SDL environment, then we make the call to the to the function, the method that we want to fuzz within the library, and then we free the memory. We compile that also with the AFL fuzz, and okay, so we compile that. Then we go on to the actual fuzzing. This is very important if you want to do fuzzing. Remember when I said that AFL is very easy to use? Well, this is the reason. This is the check it out. You just have to specify the input where you supply the test cases, the initial test cases for the fuzzing process. Then you specify the folder where you want AFL to write the hangs, the crashes that we want. This is a flag that allows you to give unlimited memory to the child process that is going to be started during fuzzing, and that we have to use this flag because I conducted my experiments on x64 architecture, and Asan consumes, other sanitizer consumes a lot of memory there, so this is why we have to do that. Another thing that we have to do is to just give a name to the fuzzer. This is not really important. And then we supply the path to the hardness function that we compiled earlier. And we inform AFL that we are going to supply the test input as the first argument. So the famous AFL screen, sorry. This is not, I mean, can you see it clearly? Sorry about that. Okay. What is a lot of interesting and geeky stuff happens here. AFL gives you a lot of information about the fuzzing campaign, but what is really important is this thing. So you want the AFL to make to fuzz as fast as possible. Here we have only 170 executions per second, which is pretty low, pretty slow. So we wanted we want a better fuzzing speed. So you can see I put the specification on the machine that I conducted fuzzing because I want you to I want to make something clear. You don't need something like a Google level infrastructure to do fuzzing. You can just start it doing at home and take a project and see what that leads you to. So what we can do to make the rabbit run faster? First thing that we can do is to enable the AFL persistent mode, and what that is AFL works like this. It gives an input, a test case to the application. Then the application processes that file, and then the program closes. And what we do here is practically keep the application open and feed it input while the execution context is still on. And that will effectively allow us to spend less time in the kernel mode and hopefully increase the execution speed doing that. Another thing that we can do is to supply smaller test cases. In my case, when I've started the fuzzing attempt, I have supplied some wave files that were about 100 kilos, and I think that I thought that I could find smaller test cases. Another thing that we can do is to run the fuzzer from the RAM disk. And the idea here is to read the actual test cases from the RAM in order to, because as we know, reading from RAM is so much faster than reading from the actual disk. And last but not the least, obviously we can run multiple instances of AFL and improve the fuzzing speed linearly. Okay, so again, the new famous AFL screen. This time we have an execution speed of 420, which more than doubled, and now I'm happy with my fuzzer. After I run the five fuzzers in parallel, I get the staggering speed of 150 and 87 executions per second, which is better than 200. And this is what I meant when I said that when TL asks you if you're stacking off, you can do fuzzing. If he sees this screen, he won't interrupt you ever. For those that are curious, I have actually employed 2 mocks in order to open multiple instances on the virtual on the server that I was doing fuzzing, so it's very easy to use. I recommend it. And the results. 11 CVs, of which I'm very proud, are my first CVs of this year. Um, if you're wondering what is with the C highlighted in red, that is because when I've posted the blog post, someone was very kind and pointed out that I had a spelling mistake, and so I've corrected it. So someone exploited someone that was trying to exploit anyone, another person. Okay, so I haven't found these vulnerabilities by doing just one test harness, and I'm doing multiple test harnesses. So I found the vulnerabilities in different module of the library, both in the audio and the video module. Another important thing is that the vulnerabilities were introduced by a commit that dated from 2006. So it's a lot of time from there. The library is still employed, and the last version of the library was affected by these vulnerabilities. So it took me a while to find something that wasn't fuzzed, but that happened because it was a very old library. Okay. I thought that it would be important to specify also the timeline, everything that happened. So I make you acquainted with the whole process. So in order to get the setup working, choosing a library and come with a test harness or come with a certain method to fuzz from that library took me, let's say, actually they're not a few days. I wanted to say a few weeks there to be more accurate. Then fuzzing the library, this is why AFL is awesome. It took me only 24 hours to come up with interesting crashes. There were like 60 crashes, of which and those crashes, then I started to filter out, and it turned out 11 interesting ones. And this is the next step: identify and trace the crashes. That took me a few hours. Then I have reported the vulnerabilities to the SDL bug platform, and they were. This is again very interesting. The development team was very quick with its response. It was a matter of few hours. They responded faster than Mitre, and that doesn't happen very often. Sometimes when I've reported other things to development and also to Mitre, usually the development team response was slower. So Mitre was kind enough and assigned the CVs for my interesting findings in a matter of 24 hours. And in 2 weeks, the development team fixed all the issues. So if you want to exploit them on an Android application that uses the library, say bye-bye to that. Also, I wanted to say, so you probably might wonder now, everything is nice and how can you actually exploit these vulnerabilities? One question might be. So these are two scenarios. They're very much similar, and they are connected because they both make use of social engineering. So you came up with an application or a mod for a game that you're interested in. So you specify a malicious WAV file that uses that. So hey, check it out, my new mod for my new game. It has amazing sounds and amazing music. Someone will try to download your game and will try it out, and then when we actually parses that file, it will go to the vulnerable function, and then the exploit will do its work. That is also true for the second scenario. So by now, if you think that okay, security research and the pleasure of finding vulnerabilities is too much of an esoteric reason to do research, here is the main reason that you want to do fuzzing. The European Union, this is an article from this year, offers approximately $1 million. Those are not for one project, but for multiple projects that are of interest, are employed by a lot of people. So if you find something with fuzzing, let's say, you might get the money. So it's a bug bounty program. That was my presentation. Thank you for your attention. one more thing, sorry. If you want to go to the full article and if you want to do fuzzing yourself, I've tried to make the blog post as much as self-explanatory as possible. I've went through the whole steps of doing so because I had troubles myself of setting up and connect every piece together. So if you also have questions, you can find me on Twitter and we can talk further from that point on. Thank you.
Okay, so if you have any questions, where's the microphone? Hi, have you used libfuzzer, and if so, can you make a comparison between those two?
Okay, thank you. Very good question. Actually, yes. I was expecting that. So paranoia is a good skill when doing security research because you come prepared. Yes, I have used the libfuzzer. I've actually used it to fuzz a project which is called Chesanta Mongoose. It's an interesting piece of software because it gives you interface with a protocol that is called MQTT, which is used on IoT devices for one. And I've used it with success, and I found something, but that was already reported just in a matter of the exact stack trace, the exact method that was crashed and everything. So it was the same finding, but he was quicker than me. But that didn't affect me very much because it told me that I'm on the right track. So keep that in mind. Someone might fuzz his way into the application faster than you. A comparison, well, libfuzzer is very much is a perfect tool for, as its name implies, for libraries. So what I've done is something like that. I've used libfuzzer. I've used AFL in order to do library fuzzing, which is not very. It's not unusual thing. They're very similar. One comparison, which is the most important thing, is that they are very similar in the outcome of the fuzzing process. So, for example, if you find a crash with AFL in let's say 4 hours, libfuzzer we have similar results, and that happens because they have the same mutation engine. So they come up with test cases during using the same piece of code, and that makes them very similar. We can discuss further. This gets a little technical, but I think it's enough. So you can use it. You can use both of them, and you'll kind of expect the same outcome. Other question, please ask.
Okay, so nice talk.
Thank you very much.
I have to announce that I will be having more than one question, so sorry for holding the mic.
No problem. Go crazy.
So first of all, in the input folder, where you placed your input test cases,
okay,
were they valid files,
yes,
or already corrupted?
Yes, they were valid files, and this is a thing that I love about mutation strategies, that will take something valid and will transform it in something bad. That's just amazing. They were valid wave sound files, and one thing that you want to do when you are employing AFL is you can supply another parameter to the fuzzing campaign, and that is called supplying a dictionary. You can supply it with an X, and what that does, it will insert certain strings that are specific to the format that you're trying to fuzz. So you can insert magic bytes or something, and that will kind of help the mutation engine to come up with something that is valid and will reach further into the code, but in a faster manner. So you'd want to do that.
Okay, and the second question, what about templates of the input files? I mean, let's suppose we have a format, and the first bytes of the format maybe is a checksum. So the first things that the target does is to check the checksum. So maybe we need, when fuzzing, to have a template and somehow to tell the fuzzer, look, generate the test case, and then the first 4 bytes, replace it and make it a valid checksum for the file.
Yes, this was the problem that someone came up with a while ago, and that's why you have generational based fuzzing. You have the set of specification, then you build the input file and you serve it to to the application. So that is exactly the reason why they come up with tools that use this fuzzing mindset. But they are more commercial tools. I mean, they are, let's say, QA oriented, because you would want to see if the developer respected the set of specification for parsing and converting different file formats. So AFL can't do that, can do that. Okay, that was a lie. It can do that. There is a fork of AFL which was developed by one of my colleagues from Polytechnica University. It's a fork that is called AFL Smart, which does exactly that. It uses the pitch framework, which allows you to specify the format in a way, and combines that with the amazing power of the mutation strategies that AFL has. So you can do that too with AFL. Please check out the AFL Smart fork and see how that goes.
Okay, great, thank you.